Alright, hello everyone. We're back for another section. This time we're going to be looking at section 4.2, exponential models. So we're going to be looking at a number of different kinds of models, but mostly we're just going to be practicing plugging in numbers into exponential functions such as this. So if we look at this one, this is the exponential growth model. So anytime you see a problem where it says you have exponential or maybe a relative growth rate, that sort of thing, this is the model you're going to want to use. So here's the example. The population of rabbits on an island is now 100, and it grows continuously at a relative growth rate of 11.7% per day. What will the population be in 14 days? Well, we can figure that out using this equation. So if we look at this, we'll know that the amount A is equal to A0, the initial population, in this case that is 100 rabbits, times e to the kt, where k is the relative growth rate. We know that to be 11.7%, which as a decimal is 0.117. And then we also need to multiply by times the time. In this case that is 14. And then from here it's just a matter of doing some calculator work. So first thing we do is multiply those numbers in that exponent. So this is equal to 100 times e to the 1.638, and decimal points really give me a lot of trouble, so bear with me a second. Well, I can't get it, but you know there's a decimal point right there. Okay, so now we say e to the 1.638 power, and when we do that calculation we get 5.145, so that's 100 times 5.145, and the last bit then is to multiply those two to get 514.5 rabbits. And then you round as necessary. In this case we would probably round up to 515 rabbits. Maybe you say, well, if we have half a rabbit, we haven't gotten a whole rabbit yet, so we just leave it at 514. It's sort of either up to you or the what the website asks you when you're doing the homework, but mostly when you're doing the quiz or test, I won't be all that picky. Okay, so let's look at another kind of example. So that was the exponential growth. Now we have what's called the doubling time growth model. This is a similar setup. We still have a population or an amount of something that's going up. Now instead of giving you the relative growth rate, they tell you d, which is the time it takes to double. And notice here this exponent is just designed to tell you how many times it's doubled. So if t is equal to d, it's doubled once, and so you'd have the initial amount times 2 to the 1 power, so you double it. And then, as it says here, the amount is twice the initial amount. If the time is 2d, so if 2 doubling periods have taken place, we would have 2 to the 2 power, and that'd be 4 because it's doubled twice. Okay, so that's kind of how this all works. So let's look at how do we use this. So first of all, in 2001, India had a population of 1.03 billion people, and it has been estimated that its population doubles every 50 years. So what is the predicted population today? I looked up what Google says the population today is. This is an old example, so it's no longer 1.17 billion, it's 1.24 billion. Okay, so we'll see what the model does compared to that. So the amount is equal to the initial population, in this case is 1.03 billion, times 2 to the power of, well, time is the years, and right now it's 2013, so that's 12 years after 2001, divided by the doubling time of 50. So that's 1.03 times 2. Do that division, we get 0.24. Again, pardon my lack of a decimal. That's a decimal point. So we have this 2 to the 0.24 power I got to be 1.18, so this is all equal to 1.03 times 1.18, and finally multiply those two numbers gives you 1.22 billion people. Okay, again, my dots are giving me trouble, but that's not too far off, right? So that means our estimate of 50 years for a doubling time isn't too bad. Okay, so those are growth models. Let's also look at a decay model. So we also have two kinds of decay models. One is the exponential decay. So that's the same, or the half-life model, excuse me. So here we're talking about, instead of the length of times it takes for an amount of something to double, we're talking about how long it takes to be cut in half. But otherwise it works exactly the same way. So here we have radon 222 has a half-life of 4 days. If a sample of 25 grams is used initially, how much will remain after 11 days? So again, sort of a matter of plugging and chugging. We have 25 grams times 2 to the negative t, in this case, is 4 divided by the doubling time. Oops, I'm sorry, that's not true. You're probably all yelling at me right there from the other side of the internet, and that's just fine. T is actually 11 divided by 4. So now again, it's just a matter of simplifying this expression. It's 25 times 2, and 11 divided by 4 is 2.75. So the new exponent is negative 2.75. We can apply that exponent to 2. The result from that is going to be 0.149. And finally, we can do that multiplication to get 3.75 grams remaining. Okay? Very good. So again, it's just a matter of plugging in the appropriate numbers in the appropriate places. So let's go down to one last example, or one last type of model, excuse me. That is continuous decay. So now again, it's just the same sort of thing, except now we're given a relative rate of decrease. So in other words, a continuous rate of decrease. So here's the example. The atmospheric pressure P in pounds per square inch decreases exponentially with altitude h in miles above sea level, as given by this. So notice, we don't have to do any plugging in. They've already done everything for us. Looks like when the height is 0, the initial, in this case we're not dealing with a population, we're dealing with an amount of pressure, but the initial pressure is 14.7 pounds per square inch if you're at sea level, and then it decreases from there. And one other thing to note here, the domain of this function is 0 to 10. So this equation only works from 0 to 10 miles above sea level. But I think if you get to 10 miles above sea level, you're pretty close to being in outer space, but that's beside the point. The question we have here is, what is the atmospheric pressure 1 mile above sea level? So we find the pressure P at by taking 14.7 times e to the negative 0.21 times 1, which doesn't do a whole lot. We take e to the power of negative 0.21, and we get 14.7 times 0.81, and finally that calculation gives us 11.92 pounds per square inch. Okay? So again, it's just a matter of taking the equation, plugging things in where appropriate. On quizzes and tests, I'll give you equations like this, so don't fret and worry that you might have to memorize things like that. Like I said, they'll be given to you when appropriate. The last topic then in this section is exponential regression. So exponential regression works an awful lot like every other regression we've done. What you need to do is identify first what your x's are and what your y's. So here, number 38, this is on page 415 for those following along. 38 says that table 5 duplicated here, gives the market value of a luxury sedan in dollars X years after it's purchased. Find the exponential regression model in the form of y equals a times b to the x for this data set. Estimate the purchase price of the sedan. Also estimate the value of the sedan 10 years after purchase. Round your answers to the nearest dollar. So we do the same thing we always have. We put the x's in list 1, these y values in list 2, and then we go to stat, move over to calculate exponential regression, and it gives you the following values rounded a little bit: 30,363 and 0.790. Okay, so that luckily, since this is the form we were asked for, these are the values we are given. So the equation is 30,363 times b, which I actually have a value for now, a value of 0.79, and that's raised to the x. So the first question was to estimate the value of the estimate the purchase price of the sedan. Well, when it's purchased, the sedan is 0 years old. So if you plug 0 into this, 0.79 to the 0 power is just 1. So this right here is our purchase price. Okay, so there's all that. We also need to keep in mind that we need to find the value after 10 years, so that's not so bad. We just find y when x is 10. So we take $30,363 times 0.79 to the 10th. And with some fancy calculator work, we can see that this is going to be $2,874.85. Okay, so there is an example of exponential regression. Just to sort of remind you of what these things look like, here we have the points that we were talking about. Value after the first year, value after the second year, third, fourth, fifth, and sixth. Here's the equation we found, and this is what it looks like graphed. So, you know, of course it's regression, it's not going to hit things perfectly, but it does a pretty good job. One thing you might say is, why do we mess with exponential regression when these things look like they're pretty close to a line? Well, the reason we don't do that is if we got a line, which we could do, but if we got it, eventually, after about, it looks like, oh, say 9 years, the value of the car is going to be negative. And that's just not realistic. These values get closer and closer to 0, but it's never actually negative. Okay? So that was 4.2. Next up is going to be section 4.3, logarithmic functions. Try to get the 4.2 done. Ask any questions you have in class. See me in my office, or send me an email as always. Goodbye.